particles, supernovas, and dark matter. Recognizing dark matter is one of the most critical trials in cosmology. 90% of the material in the cosmos is dark, but we can only conjecture about its nature. The principal candidate for dark matter is some fundamental weak elementary particles. This candidate must associate with the matter in the cosmos much weaker than the proton, a primary component of all material. For instance, everyday matter ultimately fragments towards stars. This weak interaction of dark matter reveals its alleged conduct in the cosmos when a cloud of dark matter and standard matter contracts to produce a galaxy. Nevertheless, the mysterious matter is left behind. Its weak cooperation also suggests that dark matter particles do not lose power by radiation and darkness. During cosmic development, dark particles consolidate into dark clouds, but not into stars. Dark matter is drawn by gravity alone. In our pronouncements today, we find dark matter both in galaxies' inner areas and outer regions. For example, in our own Milky Way galaxy, there is an expanding collection of dark matter in the inner galaxy, in opposition to how ordinary matter dominates in areas that include our solar system, which is ordinary material. Orbiting our Sun's dark matter also populates the exterior regions of galaxies where there are fewer stars. Dark matter controls the mean density of these outer quarters. Nevertheless, specific stars distant from the galaxy center proceed to manage their orbital velocity. If the stars followed the appearance of the dark matter, the circular quickness would decrease. As the gravity field gets smaller, the dark matter is much less intense than the starlight. Dark matter consists of weakly combining fundamental particles. We know that any particle that can survive according to the rules of physics once did live in the fiery forge of the Big Bang. All particles hold antiparticles, particles of the negative charge. Today, antiparticles are remarkably rare. Nevertheless, in the initial example of the Big Bang, each particle is accompanied by its antiparticle. There was flawless symmetry. This increased, however, as the cosmos calmed down. The primordial forge left behind limited antimatter, which is helpful for us because contact between a particle and antiparticle ends in total annihilation. The amount of remaining antimatter depends only on the strength of the interactions of the particle in the subject. Furthermore, the antiproton is actively interacting. Proton-antiproton pairs already controlled the cosmos. Many were already existing. Partners of protons and antiprotons were generated immediately from radiation at the ultimate temperatures found in the first nanoseconds of the cosmos. As the cosmos expanded and reduced, spontaneous creation held almost all at the antiprotons obliterated with protons. Nevertheless, luckily for us, some protons are left to create the material cosmos. This significant annihilation created the cosmic microwave background that we now measure, the heat left over from a fireball at the origin of the cosmos. The identical philosophy pertains to the dark matter particles, that most were obliterated. At this period in our search of the dark side of the cosmos, we saw a remarkable event in how the laws of nature appear to work. This sort of discovery always makes cosmologists feel great. Nevertheless, in this case, far more were left back because certain particles combined so weakly. There was neither reason whatsoever for this eventuality. Nature commands it. Weakly interacting particles can value all the observed dark matter if their interaction strength is characteristic of the weak nuclear force. They need, of course, to be long-lived and associate with a potency like this of the neutrino. This seems a tangible interaction to be required for such particles. The interpretation of the origin of the weakly interacting dark matter soon shifted to more compelling. A new hypothesis called supersymmetry was revealed that postulated the existence of hundreds of potential dark matters. In the new supersymmetry hypothesis, any applicant for dark matter must be a weakly interacting particle. Only one of the competitors can be the proper form. In particular, it needs to be the lightest of the supersymmetric particles to be adequately steady. The remainder of the candidates lives for bare nanoseconds. We are now close to the path of these particles. One of the principal goals of the Large Hadron Collider performed by CERN is to hunt for proof of supersymmetry. The accelerator, which runs for 17 miles, will smash one-sided jets and high-energy proton-antiproton to form collisions. The impact releases energy that, in turn, produces waterfalls of quarks and other short-lived particles. Force must be maintained in the contact. Seeing a stream of particles emerges in one direction with no similar stream sprang out in the opposing direction would present evidence for supersymmetry. As noted earlier, there are many candidates for dark matter. Fortunately, the most common class of hopeful particles hails from the hypothesis of supersymmetry and is expected to be visible. Granted that supersymmetry is correct, the most graceful supersymmetric particle is supposed to be durable and can judge dark matter density. Supersymmetry is driven by hypothesis but also by empirical discussions. One of these is the running of the coupling constants of the underlying forces. The constants are vastly distinct from all other today, but this was not the situation. Today we exist in a low-energy universe, but at very great energies. The weak nuclear force grows much stronger than we extrapolate the strengths of the various forces included at low 100 gigaelectron volts energies. They appear to gather near 1,000 trillion gigaelectron volts. Supersymmetry needs concentration at precise energy, called the order of great combination of the elemental forces. As we observed earlier, this order granted the stimulus and physical setting for expansion. Again, the applicant particle must be dull and weakly interacting. It is related to the neutrino and is the complex counterpart of a distinguished particle such as the photon. Neutrinos are in thermal stability at the high temperatures of the ancient cosmos. As the temperature dropped at the origin of the cosmos, a relic density of all the constant particles persisted, the weak nature of impartiality. No self-interactions occurred in an excellent relic density in opposition to that emerging from actively interacting particles. Remarkably, the relic density generically provides an almost critical density of dark matter. For a weak-like cross-section, the cosmos was previously at energies wherever supersymmetry prevailed and a breeding ground for supersymmetric dark matter. This means matter and antimatter. The primordial forge must have formed pairs of weakly interacting particles and their antiparticle companions. Particle theory gives us nominees for these particles. None have, however, been perceived, which is a lesser barrier. If one of these distinct particles is constant, then its weak interactions support a significant survival portion. Today, these could be the obscure dark matter. Now we can explain why there was so numerous dark matter particles left over from a single Big Bang. We are attempting to obtain this dark particle by utilizing heavy machines using state-of-the-art technologies like the Large Hadron Collider. But this scheme alone costs €5 billion. There is another €5 billion upgrade this year in 2021. The collider has put thousands of superconducting magnets to create a particle accelerator 5 miles in breadth in its circular ground design. A device like this can grow so precious that we reach the physical limit for such analysis. Fortunately, therefore, we can still use the cosmos itself as a particle accelerator. In the expanses of the cosmos, particles are destroying each other beyond space. Consequently, we are attacked with dark matter. About 10 million particles per square meter per second pass within us. As we will shortly see, we do not have to create a supercollider. The cosmos itself presents a poor man's way of hunting for dark matter. The dark matter that besieges us is created by the annihilation of particles as if diving into a supercollider in the faraway cosmos. How is this an attractive place? Once in the incredibly early cosmos, the dark matter particles were far more diverse and annihilators were common. Today, the density is moderate and annihilations of the dark matter particles are unique. Nevertheless, although rare, because the capacity of all galaxy halo is so vast, annihilations may yet lead to a detectable sign. Consequently, our best method is the wreckage from particle annihilations. Conventional particle masses are supposed to be on the order of the power scale defined by our current supersymmetry hypothesis. This system is between 100 and 1000 proton masses. The acronym for these weakly interactive massive particles is WIMPs. While annihilations take place, they create a shower of energetic elementary particles, most of which decline quickly. The tangible outcomes are high-energy gamma rays, proton-antiproton pairs neutrinos, and electron-positron pairs. All of these are probably discernible with future operations. The prophesied flux depends on the density of dark matter. We assume the regional density in the solar neighborhood from the revolution of our galaxy. It amounts to 1/3 of a giga-electron volt per cubic centimeter. Around 10 million per square meter per second pass through the Earth. With such a notable influx, we can attempt to identify the particles, indirect discovery procedures directly. This tremendous flux of weakly interacting particles illustrates the quality of the research challenge for the prospect. The dark matter particles, although very weakly communicating, do irregularly collide with atoms in a machine. The detector has a bizarre sensitive matter to pick up a slight trace from particle contacts. Nevertheless, this through detection does not operate with other sorts of dark matter annihilation, so we practice secondary detection as well. This technique picks up the irregular dark matter annihilations in a galaxy halo. When these annihilations happen, they create an energy loss in the style of both gamma rays and energetic particles. Indirect evidence of dark matter. Our discovery of these as indirect evidence of dark matter, both varieties of detection, provides us hope to determine the dark matter problem. It is also a charming story of method and technology. So let us examine more closely both procedures, beginning with direct exposure. There is no replacement for direct exposure of the dark matter particles. The flux of such particles on the Earth is comparatively large. Of course, the interplays are weak, but stretchy recoils leave possibly detectable signs and adequately large portions of the target element. The nuclear recoils energy and irregularly ionized detector nuclei. Detectable signals involve seeing hints of electrons and ions and oscillations of vibrational energy in the atomic lattice arrangements of all solid matters called phonons. However, there are actual experiences, mainly emanating from cosmic rays hitting the indicator and producing neutrinos to see the WIMP signal. So one has to overcome these experiences. The only way is to go far under. Disused areas in mines have been applied. One of the most useful is in Sudbury, Canada, at a depth of 3 kilometers. Until lately, detectors in clandestine laboratories have been kilogram scale, with sensations to elastic scattering cross divisions down to a 10 billionth of a barn, or a 10 to the power of negative 24 centimeters squared. 1 baryon is the regular interplay cross-section for average atomic nuclei such as protons. It compares to a valuable area for scattering amounting in the square of the standard radius of a proton. These are the continued nuclear interplays for a meaningful density of WIMPs bearing from the real early cosmos. The regular cooperation strength must be less than a billionth of a barn. This is the area of weak nuclear interplays. These are the results that include neutrinos. The experiments have directed out WIMPs in this regime. Nevertheless, the supersymmetric model parameters provide a notable dark matter mass over a wide range of interplay strengths below regular weak interactions. If dark matter cross-sections, one can own up to the 3 orders of magnitude deeper than current test destinations from WIMP searches. The opinion has shifted the goalposts, and more delicate experiments are demanded. The only way ahead is to have more enormous mass detectors. H-ton or even kiloton detector masses are expected to examine the complete range. This is the intention of the new age of trials that use detector matters as varied as liquid, argon and xenon, or crystal germanium. One exciting addition realizes that dark matter may control fine-scale construction on the solar system scale. The dark matter is cool because individual particles have substantially no random motions if fluctuations are started. Initially, the dark matter answers to gravity on scales much less than these of galaxies. Most small clumps are supposed to have Earth masses, but are greatly more distributed than a planet. Consequently, the Earth, as it encircles the Sun, hardly runs into dark matter clumps. Dark matter is so diluted that it has no immediate control via influence on the Earth. However, investigations searching for the weak sign from immediate exposure would find an annual inflection of the tricky signal. Streams of dark matter in the solar community emerge from the unfinished tidal separation of dark matter masses in galactic orbits. One through-exposure experiment at Grand SASO, a deep secret laboratory in Italy, uses this designation and is the only test to report a claimed exposure. This venture, called Libra, employs a vast vat of sodium iodide and hunts for light and elations. Other groups discuss their results. However, using different techniques and more sensitive experiments, a window lives if the neutrinos interact coherently. In this case, the interplays depend on the regulation of spin of the end atomic nucleus, which can be essential for nuclei with odd numbers of particles. Sporadic experiments are susceptible to this synergy. The most critical problem is hydrogen. The Sun contracts such WIMPs, and its composition is very lightly affected. If the volume is around 5 proton masses, the WIMPs take a long period to settle into the heart and obliterate. The general lower guess on WIMP mass is about 50 proton masses from accelerator limits. Nevertheless, some designs permit these more moderate masses. Low-volume WIMPs turn out to be a potential means of mitigating Libra with most other analyses. There are two methods for estimating the interior temperature in the Sun. One includes identifying the neutrinos released in the thermonuclear responses that occur in the solar core. The growing detection of solar neutrinos has proved that thermonuclear burning of hydrogen commands the Sun. It also stays at the central temperature to great accuracy. Another test involves identifying seismic quakes in the Sun. These WIMPs scatter with cosmic particles and somewhat alter the temperature profile by redistributing the thermal energy. Helios seismology measures very slight fluctuations of the Sun. The frequencies of the standard methods depend on the sound exchange time in the Sun and hence on the temperature form. At present, our most suitable model of the Sun cannot consider for the Helios seismology issues. The difference is only about 10%. However, the result is that despite the Sun being the nearest star and exquisitely well examined, we yet lack a comprehensive knowledge of its composition. Dark matter may conceivably have a part to perform, although it is considerably more likely that the difference rests in something as ordinary as our modeling of disturbance inside the Sun. As we explained earlier, our detailed disclosure of dark matter is achieved by tracking the pieces that spray off other particles when they conflict with dark matter. When dark matter particles of 100 to 1000 proton masses conflict with other particles, the annihilation provides energetic gamma rays, neutrinos, positrons, and antiprotons. All of these are distinguished signatures that can be discerned upon a known framework. High-energy positrons that appear from collisions, for example, are particularly beneficial since they are a rare segment of the galactic cosmic rays. Moreover, all these byproducts of the impact look distinct from remains of the dark matter, since those remains cannot exceed the WIMP's mass. This diversity leads to a point in the energy frequency of high energy. Photons are particles. Other particle experiences are blind to WIMPs, so the backgrounds do not display any articles that might show the presence of WIMPs. Despite the various competitors for the most vivid supersymmetric particle, we understand it is annihilation, cross-section to high efficiency. This arises from the claim that the WIMP's value for the density of dark matter. If the cross-section is too level, there are too numerous WIMPs. If it is too high, there are also few WIMPs. This limitation occurs because annihilations in the entire cosmos made the surviving body of WIMPs. The WIMP particle so far is undetected, which of course indicates that its mass is unexplained. However, the supersymmetry hypothesis specifies a series of cross-sections at any provided mass. This series spans some 3 factors of 10 miles. The permissible mass reach extends from simply 50 gigaelectronvolts to 1 teraelectronvolt. The answer is that tests must include an extensive range of delicacies to have any venture of discovery. However, discovery at some level is confirmed if the lightest supersymmetric particle is the companion of one of the perceived particles, which themselves are arranged according to their rotation and mass into particles, for instance protons or fermions, which carry electrons and quarks. The positrons afford a good sign because universal ray positrons are rather limited. The local dark matter density measures the positron flux. The gamma-ray flux is also an attractive sign. The halo is clear to gamma rays because the density of dark matter is greater. Near the core of the galaxy, the gamma-ray flux is increased. There are gamma rays generated by the interplay between universal rays and interstellar gas. There are also positions in the universal galactic rays, but the dark matter sign should reach out. Its positrons and gamma rays have a different combination of energy defined by the mass of the annihilating particle exposure of wastes in both the positrons and gamma rays corresponding to the associated backgrounds would be proof of dark matter particles. Tests carried out far away above the Earth's exterior have been conducted to study positron and gamma ray evidence. It is essential to go into space because there is too much corruption by cosmic rays communicating with the Earth's atmosphere. So far, there is no reliable evidence of a signal in either gamma rays or positrons that could be from dark matter. There are, though, hints of potential exposures in both cosmic ray positrons and scattered gamma rays. For example, high-flying balloon trials reported an unusual spectral bump trait in the positron flux that is not defined by the featureless secondary spectrum of positrons created by cosmic ray interplays with interstellar material. The dark matter particles obliterate into a rain of debris. Consequently, the annihilations generate a positron feature collected around 10% of the particle mass. However, the information was not persuasive. The possibilities are vital. It is too rash to make much of any potential annihilation sign. New investigations are underway. A new trial on an Italian-Russian space satellite propelled in 2006, called Pamela, takes information that presents a much improved determination in the positron flux after several years in orbit. Early proceeds help the unusual spectral bump, but the interpretation of this article cannot necessarily be described as a dark matter signal. The energy is much greater than anticipated from the simplest speculations. The alternative solution appeals to a nearby pulsar in the constellation of Gemini called Gemini, an abbreviation for a Gemini gamma-ray source that is perceived to be a source of vital energy gamma rays. More data will be required to explain the preliminary results better, and it will be required to find complementary signals. The most encouraging of these arise from distributed cosmic gamma rays. Gamma rays from space ought also to be identified. Indeed, the Milky Way glows, and gamma rays are created as cosmic rays crawl through interstellar gas clouds. In summation, high-energy encounters between protons create gamma rays. The Compton Gamma Ray Observatory identified an excess distributed flux of gamma rays from the inner galaxy. The energies of these gamma rays seem to be greater than anticipated from the flux foretold by cosmic ray interplays with interstellar gas. More unusual decay courses may be shown than would be possible with cosmic ray protons. This is precisely what is prophesied for the WIMPs. The possible decay channels for WIMP has no annihilation, including extensive quarks measuring up to 5 proton masses. The resulting gamma rays from decays of these quarks are more dynamic than those created when protons crash with other protons. First, though, the data needed to be established. The gamma-ray large-state space telescope named Fermi, after Italian-American physicist Enrico Fermi, was started in May 2008 and should implement the required confirmation if WIMPs are the elusive dark matter. The Fermi telescope increases sensitivity by 100 over the prior gamma-ray satellite venture flown on the Compton Gamma Ray Observatory. This exercise will significantly advance the current data. It should be likely to confirm or reject the existence of the potential signal from obliterating WIMPs if the initial preparatory results were to be understood as due to WIMP annihilations. A critical issue occurs concerning the power of the predicted gamma-ray and positron signs. What has been perhaps observed is far exceeding extensive than expected. The quest for dark matter. In our quest for dark matter, cosmologists also need to battle with two different sorts of sensations that can effectively disclose the ambiguous particle. One of these is the clumpiness of dark matter. Besides, a moment is how dark matter spikes while it is in the proximity of a black hole. There is a resolve to this predicament at the slightest for the gamma rays. The clumpiness of dark matter is linked to its capacity to provide the earliest design for the detected wide-scale structure of the cosmos, which occurs later in the very ancient history of the cosmos. The WIMP particles decoupled from the radiation, which suggests that in the recent past, the WIMP particles were freezing. That is, they possessed negligible arbitrary speeds continuing from their thermic origin. As the cosmos developed, random acts of particles would decline and the WIMPs would grow cool. This is the connection between cold, dark matter and large-scale construction. The complete clustering features can be represented in computer simulations if simple models for galaxy formation are used. Nevertheless, the cold, dark matter candidate has not, however, been identified. It remains a theory. One ambiguity in computing the flux is the size of the clumpiness of the dark matter. For now, we operate on the premise that the annihilation rate is equivalent to the square of the density. Mathematical simulations of galaxy formation display that halos are clumpy, with up to 10% of the dark matter existing in clumps, appearing in a substantial increase factor for the annihilation flux. The theoretical modeling of the halo informs us that it is highly clumpy in a clumpy halo. There are considerably more particle impacts and annihilations than in a soft halo. It is tolerably simple to consider the observed gamma-ray flux in this way. The positrons cannot be readily defined because positrons usually scatter as they propagate in the interstellar medium. The detected positrons cannot come from far away and not from the inner galaxy, where the improved consistency and clumpiness of the dark matter boost the perceived flux. The positron story must be more complex, depending on how the positrons produce and accumulate. The flux of the annihilation sign is susceptible to the smallest size, about the size of an Earth mass for typical WIMPs. Nevertheless, interplays with stars will tightly confuse many of the clumps, entirely depending on their orbits. Clumps with orbits highly likely to the disk should remain. Low-mass clumps are barely visible via their annihilations beacon, which is available by the second detection method. We have simply considered black holes shortly so far, but now they have grown an indispensable factor in distinguishing dark matter as well. Dark matter is collected in the region of a black hole. Furthermore, relic bunches of dark matter form around growing black holes. Dark matter particles are improved in representation in the nearby increasing gravity field. Consequently, the dark matter density is developed near the black hole. So, as the annihilation signal, we initially need a summary of black hole generation. Their formation needs matter that can dissipate energy as it deflates. Baryons can do this by radiative cooling, except dark matter cannot, so it appears not to become a matter for the black hole. Nevertheless, as the baryons aggregate to create the black hole, some dark matter particles constantly are deceived by the growing strength of the local gravity field. Consequently, the annihilation flux may be significantly increased near a massive black hole that develops in the nucleus of a forming galaxy. These black holes are supposed to form using the accretion of baryons onto a seed black hole, one that is only growing. The seed is produced from the wreckage of massive stars. This is not an exclusive development possibility. Furthermore, a different route to massive black hole production is via runaway amalgamations of stars. We see the phase of black hole growth diffusely as the importance of gas accretion. The luminosity of the black hole progresses as it is refueled by slipping debris. We infer the number of fueling considering this is the aspect that power quasars and energetic galactic nuclei. Finally, we have additional clues regarding how black holes form and their relation to dark matter. One is that supermassive black holes typically show up in the spheroid, our impressive bulge at the hearts of galaxies. This seems to be a cosmic aspect. A large section of the mass of a spheroid is dark matter. When the primary black hole formed, it must have concentrated the confined dark matter in its proximity. The weakly interacting dark matter returned to the deepening gravitational potential. About the black hole, a density spike of dark matter appeared within the gravitational field of influence of the black hole. In waiting for dark matter spikes, we simply recognize that black holes form with a wide variety of masses, minor dark matter clouds in which baryons can moderate amount to about 1 million solar masses in weight. The most extensive resemble to giant galaxies. The analogous black hole masses vary from 1,000 solar masses to a few billion solar masses. All these black holes manifest dark matter spikes or cusps. Black hole mergers terminate those nearby cusps of dark matter. Therefore, it is unclear, for example, whether the 3 million solar mass black hole at the heart of the Milky Way galaxy occupies such a. If this were the problem, the annihilation speed would be significantly improved in the vicinity of the central black hole, and this annihilation time would be detectable via gamma-ray emission. Nevertheless, not all black holes travel to the heart of galaxies. For example, during the hierarchical development of the Milky Way, which included merging clouds of dark matter and baryons, the smaller black holes did not blend into the inner black hole. These intermediate mass black holes reside in orbit in the central galaxy. They are everywhere, and they are possible targets to identify dark matter spikes. Black holes are constantly ejected from the cores of galaxies, possibly into intergalactic space. A merger of two black holes frequently concludes with a one-sided burst of gravitational radiation. The net effect is that the merged black hole experiences a kick in the reverse direction. Since momentum is conserved, the obtained velocity is often open enough to dismiss the black hole from its host galaxy. These intergalactic black holes should retain some dark matter in their environment, although merging tends to minimize any initial spike of dark matter. The spikes should last around intermediate mass black holes that have not been known to merge. These 1,000 solar mass black holes are evidence of the original clouds within the earliest stars that appeared. The most extensive of these clouds would have frozen as they emitted radiation from hydrogen atoms induced by encounters with other atoms. This so-called Lyman alpha emission and the effective cooling compared with this type of cooling, which demands only atomic hydrogen, would have aided gas secretion rates and developed protostars. The enhanced growth implies that the first stars were undoubtedly massive. Massive star destruction facilitates the possible formation of thousands of solar mass black holes. The most extensive black holes in the cosmos power up ultra-luminous quasars. These are the most fundamental black holes, and their sizes pass a few billion solar masses. They are found in the initial cosmos at a redshift of 6 or exceeding. These black holes are so extensive and in position so early that intermediate mass precursor black holes must have survived to explain their development. These intermediate mass black holes could be the lost link between primordial clouds, actual ancient states, and quasars, which developed later throughout the most central black holes, as noted. Regrettably, most of these more miniature black holes failed to blend into the bigger ones, and so are leftovers. In common, the merging manner is notoriously unproductive. Anyway, many smaller black holes would be discharged by recoil in the formation of binaries, black holes in orbit about each other, and then quickly be disintegrated as the more extensive systems progress. Nevertheless, as many leftover black holes survive than are destroyed. Furthermore, these are the remaining black holes that we believe populate our halo. These intermediate mass black holes are assumed to value as much mass as the interior supermassive black hole in a galaxy. Most relevant for our purposes here, these intermediate black holes maintain their original dark matter spikes. Thus, these black holes are prime candidates to consider for gamma rays and neutrinos created by annihilations of the dark matter now in the form of spikes. Furthermore, if seeing and identifying dark matter is not challenging enough, cosmologists are also engaging with dark energy and with more surprising findings.
Marinina Tura Laraba Kopana Lana Tula Lana, Marinina